So let's examine this equilibrium situation using a very important reaction where we are going to synthesize methanol in an experiment. So we do that by reacting carbon monoxide in the gas phase with hydrogen in the gas phase to form CH3OH, which is methanol. And of course, methanol is a very important liquid fuel. But remarkably, if we start with an experiment in which we have 1 mole of CO and H2 in a 10-liter vessel, that's 10th molar of both CO and hydrogen. And at this juncture, we have no product. If we allow the reaction to go forward, we recognize that at the beginning, we have the concentration of CH3OH equaling 0. And as the reaction proceeds, it proceeds producing more and more of that methanol until it reaches a critical point. And we can map this out because if I have carbon monoxide in the magenta color and I have hydrogen in teal and I've got my product ethanol in black, as I watch this progress, the concentrations of CO and H2 decrease because I'm converting CO and H2 into the product molecule that is now increasing with time. But then a remarkable thing occurs. Namely, we hit a point where the concentrations of all of the species stabilize. That is, they do not change with time. And that's the point at which equilibrium is reached. And in particular, as soon as we hit that equilibrium point, we know that the back reaction converting methanol to carbon monoxide and hydrogen exactly equals the forward rate converting carbon monoxide and hydrogen to methanol. But this gets more interesting because we can change the experiment around and we can start the conditions for which methanol is present at a concentration of 1 mole, and it's 1 mole per 10 liters, which gives us 0.1 molar. And if we start the reaction with absolutely no carbon monoxide or hydrogen in the system, and then we let the reaction proceed. And remarkably, what happens now is that the methanol converts back to carbon monoxide and hydrogen. And we can see that because CO and hydrogen are increasing at the same time that methanol is decreasing. And again, we hit this magic point, the equilibrium position, in which the concentrations are no longer a function of time. That is, we're producing the product methanol at exactly the same rate that methanol is breaking up to produce carbon monoxide and hydrogen. So let's run one more experiment. We'll call this our experiment number 3, and in this case we have all 3 species at 1 mole in a 10-liter vessel, so a 10th molar, but they all start out with the same concentration. Now when that occurs and the reaction proceeds, now the concentration of methanol decreases and the concentration of H2 and CO increase until we again hit an equilibrium position. And the question now is, everything's initially changing, concentrations are changing, but when we hit that equilibrium point, the question is there any constant that defines exactly the equilibrium position that that reaction will seek before it hits the equilibrium site?